Okay, wait. That song is now is streaming on the
yeah.
Anyone, any style is fine for me.
Okay. Yeah. All right. So
and
maybe
that's is also recorded.
Yeah.
Okay.
Okay. Yes.
Yes.
All right. So
okay.
Yeah.
Can you see that?
Yes. Okay. So right.
Wait a moment.
All right. Okay. So
Anytime.
Okay. I think another. Yeah. So
when you are available, that's anytime.
Yeah. So I think maybe I can. We'll start. I'll introduce you, and then people will slowly join.
Okay. Good.
All right. So we have a very special speaker today, and it's really my pleasure to introduce Professor Yutaka Shikano from Gunma University. He's in the Graduate School of Science and Technology at Gunma University. And so Professor Shikano has worked on many different areas of physics. He is a very versatile physicist. I mean, he has worked on foundations of quantum mechanics, general relativity. He's worked on quantum optics, photophysics, and he's worked on quantum computing as well. So has really worked on a very wide range of problems. And he is currently an associate professor at Gunma University. And before that, he was in Keio University in the IBM Quantum Hub there. And he also was at the University of Tokyo as a project associate professor. And he did his PhD and postdoctoral studies at Tokyo Institute of Technology. And so he has very kindly agreed to give a talk to us today on quantum random number generation using a quantum computer. So how random numbers can be generated using a quantum computer is the subject of his talk. And so with these few words, I'll request Shikano-san to give his talk. Shikano-san, please.
Yeah, thank you so much for kind introduction. And also thank you so much for giving me this opportunity to give the talk on that. It is my great pleasure. I met when I first time met Das-san, Professor Das in that at the Tokyo Institute of Technology, when I was already left on this, the Tokyo Institute of Technology as well, but that he is a great contribution to our graduate university. But unfortunately, today's in that name of the will be changed of our university in the near future. Yeah, that's the defined. It's the English name we don't know yet, but in that the Japanese name is was officially. Is that okay? Good.
Yes, it's okay.
Yeah, it's okay. Good. And that's I'm very happy to give a talk. Then that's right now I'm currently working at the Gunma University. It's the sort of northern side of Japan, and also I'm working with the Chapman University in California. Its location is near Los Angeles, or that's the one. That's the Chapman University has the Institute for Quantum Studies, funded by Professor Yakiro Ahanos. and Jeff Truxton, is that they are working on that quantum foundation work. Then that's today's mixing work on the quantum foundation and the quantum information science. Then today's title is quantum computer health check via the quantum random number generation. Then that's a talk. When you have any question and any opinion, please raise your hand or just writing your question in the chat box. That's I will check. I check always on the chat box as well. Then, okay, why? What happened? Then those firstly is that recently is, as you maybe know, is that the quantum computer has the fascinating in the world, and that's I'm not sure that's this recent data or not. It's several type quantum computer has been developed. For example, is a superconducting qubit type, and the electrons being trapped by the cold atom is a photonic qubit. It's just any time of that qubit, physical system, physical devices, is that seem to be have a scalability of building up the quantum computer. Then now is that greatly working on that scaling up of this quantum computer as well. Then the question is that the punchline on the timeline is that as well, like that. For example, IBM announced that this last year is a 443 qubit system is now available, but I'm not sure. But it's the question is why do we need it? It's a multi-qubit system, multi-qubit quantum computing devices. That's so many people. Will be answer is, why is that the not so good system? It's so many people. The answer is coming from that. Quantum computing has a key potential, several potential applications. For example, is a quantum chemistry calculation, optimization, is a machine learning, material science as well. It's several kind of that qubit number is needed, and also it's a security for security purpose to breaking down is RSA cryptography. Is that we now is this is based on factorizing prime number factorizing problem. That's kind of the qubit. It's a few hundreds qubits is needed. It's that we have already known. But now then that's we now is developing on the scalable quantum computing devices. It's now is academia and industry companies now is try to attack in that large quantum computer. But is that needed? This is my question. Is that okay? That's we have already known that several people say it's several potential key application. But honestly speaking, on the quantum computing devices, just only one qubit has that great power for application. That's one. It's one qubit application. It's the quantum random numbers random number generation. It's one possibility key. This is because that's for constructing the ultimate security purpose. This is the one most important application for quantum computing. That's to breaking down cryptography, a current cryptography technique. That's RSA. That means of the RSA security. RSA security surely is so many qubits, and large scale quantum computing devices can attack can break down RSA cryptography system. And also now the cryptographers is try to building up post-quantum cryptography system, such as the lattice-based cryptography system or just a quantum key distribution. That means quantum cryptography. It's now is also that developing on our quantum technology system. But now is that they're forgetting about that's the base on that cryptography technique as well. Oh, this one is a secure random number generator. Any kind of cryptography technique, we need secure random number generator is that's needed. But one possibility is that the pseudo random number generator, such as the Mersenne twister, or just the Mersenne twister is the one most commonly used of that the random generation of the random number in digital computer. For example, when you use that Python program, it is a function of the land. Land is based on that the background system is a Mersenne twister is technique to generate it as a pseudo random number generator. This is the base for our secure random numbers. And also the physical random number generation is, for example, is the CPU heat generation using the helping that the heat temperature of the CPU temperature. It's that the base is that can generate of the generation of the random number. It's that this we call that the physical random number generator. It's also that the quantum random number generator is that the one possibility to secure a random number. But except for the quantum random number generator, is that we based on that such kind of system like here. This we have to the inputs like here. Is that some of the devices is any input in that, but the same input, but the different outcome. This is the way we want to create is a true random number generator. This is the structure is that the same input, but the different output is that is probabilistically is that the output is that required. But the pseudo random number generator is needed for that now is additional input is required. Is the additional input required, for example, some of that actual digit number or in the physical random number generator cases, is that the heat temperature of the CPU, for example. Such kind of cases that we call that such kind of input, additional input is that we call that a seed. When the seed was hacked, that the output number is also hacked. Then when we want to create is a true random number generator, is that we have to that the seed rest mean on that no additional input is that we want to create on that random number generation output. Such kind of structure is needed like that. Then seed is or just the seed is required to be unpredictable. Unpredictable means on the two meaning is that computationally it's not to be hacked, or just in principle we cannot be hacked. That's kind of that one possibility. Then why is that this so important on the additional numbers hacking of the seed? That's the history of the hacking of the pseudo random number generator is that there's always hacking in that seed. For example, in the 2014 and 2015, is in Russian casino problem, is that the casino is that also that so many money is that the transit. Then, but some people hack on the seed on that some of the casino, and also Bitcoin is that several kind of cryptography money this cryptography money is also that is about based on that seed hacking. Is that this is that a huge secure problem or just economical problem as well. And also it's that Sony PlayStation, that's the Japanese many important the game player. Is that this Sony is that PlayStation 3 is that failed in 2016 and 2017, such kind of that. This is that the leakage of this output in that voltage of that this is the computer. That's the PlayStation. That's we can easily hack to that random number. Then that's some of the gaming of the scenario or just the communication of the report. Any kind of system was hacked. Then that's the to construct it. That's a secure system, more secure system is that we can seed of that seed hacking. Then seedless random number generator it's needed. That means all the unpredictable random number generator, and also that means all the true random number generation. That's the one of the possibility of this true random number generator. It's that's the quantum random number generator. That's the required maybe. This is because that the quantum random generation cannot be simulated by conventional computational technique. That means it's not be hacked. Then that even if so, that the quantum mechanics does not needed. If that's the hacking of the quantum random number generator, that means that the quantum is our quantum mechanical world does not be require does not require probabilistic structure. Then that even if so, that the quantum mechanics does not meet the probabilistic structure as well. Then that's this question is based on the quantum foundation topic. That's why I'm interested on the quantum random number generator. Then that's my motivation on that my C3 had on the foundational work on that quantum random generator. This foundational topic applied to is a quantum computer health check. That's now is today's talk. Please imagine of the health check in the recent year. Recent years that the health check is that we can imagine that kind of one is unfortunately it's the COVID-19. On that this is we have already known that the health check already. For example, is in that every day is we check on the physiology temperature, physiology body temperature as well. This is we already always every day we can check on the health, our health, and also when we feel that a little bit fever or something, that's a little bit, oh my God, such kind this in the antigen test is also now is available. And also the PCR test is that's a little bit more to be accurate of this our health check. Then that's kind of the image of the health check in our human's health. But our human health, our need on the human being health check, it's easy to be imagined. But hardware side means on the our smartphone, conventional computer, or just even that's a quantum computer as well. This is kind of the computational devices and or just experimental equipment. Is also that we need a health check. Such kind of that. Please imagine of this our computer is booting. When we boot or just start on that turning on the switch on our conventional computer, and that's some of the booting window is open. that's kind of some of the monitor proceed on the file system. Some program is running, then this is okay. This is a check. That's kind of this kind of checking procedure. Our computer is a health check system. It's now is applied to that. This was used. It's used. Normally used in our computational devices system. In that health check. Then how about today's question? How about the quantum computer health check? That's normally is that quantum computer is that all is required is every day or any time is can compute is properly, hopefully, but is that possible or not? Then we have to check. This how to building up on the quantum computer devices. For example, is a minimum requirement for the quantum hardware is that Professor David DiVincenzo proposed that 2000 in that some of the, as well we know, it's a DiVincenzo criteria. It was proposed. Then, for example, well-defined qubit, initialization to the pure state, or universal gate sets in that can be operated, and also qubit-specific measurement, and also long coherence time is required of each qubit. Such kind of that's the system requirement is what's proposed. And also, is that how to quantify this on our hardware system is that some of this several proposal was already known. For example, is that the quantum state tomography and also the quantum process tomography as well. And in the inspiring this one is that the randomized benchmarking. This is normally used in our quantum computing system. And also, where is the pointer is? Okay, gate set tomography was already proposed, but several kind of assumption is required, and also information of more information, less information. That's kind of some of this, how to say, it's how much information do we need to be get from that quantum devices? That depends on the requirement. Is that we can change on that some of the tomography or just the quantification technique. It's also any time is what's changed. Then that's some of this requirement is required in our quantum computing devices. Yeah. Do you have any question? No? Okay, good. Maybe no, it's that I will continue on that my talk. And also to compare, it does a quantum and the classical computer. It's a classical computer system. It doesn't mean the conventional quantum conventional computations, digital computation system. Is the program was already set. That's the input to the black box. This output is that's the result. This is the classical bit in that classical bit representation is required. In that output is also that the digital bits is the representation is that as the output. And also to compare that's the conventional computer to be quantum. Even in the quantum, this is the structure is the same. But what is the difference is on that some of the input to be the input output relationship. According to that the input on the digital bit on the program, that's the deterministic output of that mean of the deterministic outcome is this is standardly was used in that classical conventional computer. but the probabilistic outcome was output. We want to call that's a quantum computer as well. Then that's the functionality of to consider functionality of quantum computation. It's maybe is that a probabilistic outcome structure. That means also to be checked on that this functionality is that random number generation checking. It's also good checking procedure of this our quantum devices or not. Then that's we try to do. That's strategy. That's the digital system input is the same. This outcome is a 0, 1, 0, 1, 0, 1. That's the sum of this digital output. This digital output is that randomly generated or not. This is that we want to check to that from now. This is the most simplest, the simplest algorithm of the quantum random number generator. Is that mean on? I think it's the simplest quantum algorithm. I think. Then we have to set on that the initial state. Initial state in that we have to the initialized state is the 1 qubit. 1 qubit case is that's only that 0 get. And get 0, and also that's to generate it to apply same input mean on the same gate to be applied in this state. That's mean the Adamar gate. Adamar gate cases, that's final output 1 over square root 2 is 0 plus 1. That means also the superposition state. Then that's finally we projected measurement. That's the output of output number digit of the 0 and the digit on 1. That's an equal probability, and that means also 1.5. That's the probabilistic structure essentially induced by measurement. But the projected measurement is that this is also the same procedure. Then mean also the gate in the projected measurement, Adamar gate projected measurement. In that same input mean also the initial state in that the initial state, and also that the Adamar gate projected measurement. This is also the same path. Then anytime on essentially this is that the true random number generator is a structure. Then we want to check. We try to that how about the simplest algorithm using that IBM Q. This is when I was Das-san introduced me when I was working at the Keio University, and by 2 years ago. That's under the IBM Q quantum network hub. Then that's okay. When I'm working at the Keio University, I firstly tried to use IBM Q machine. Okay, we try to to apply this simplest algorithm. Such kind of case, that's a cloud computation call we send on the IBM Q machine in that at that time in that Watson in that in near New York City. Such kind of case in that Adamar gate measurement, Adamar gate measurement, Adamar gate measurement. This is the parallelly is the 5 qubit is to be simultaneously applied. Then that's the output we can get it. Such kind of cases. That's 5 years ago. Oh, sorry, 4 years, almost 4 years ago. We tried it. That's a system, and that's the devices number is that some devices. Such kind of cases, output of this result in this 5 parallel qubit. Oh, it's not so. That's the result was shock. This is because this is not so uniformly distributed. Oh my God. That's kind of that noisy output. when I was first right time to be used IBM Q machine, this is the requirement. And also how about the quantum 20 qubit machine cases? Okay, that's KO contracted with that IBM. Then that's good machine is the best machine was supplier, I thought. But we try to do the same thing. In the 20 qubit parallelly it was used. Oh my God! In the also same system, same noisy result was seen. Then that the current quantum computer do not provide unbiased random number generation. Oh my God! My projection might be over. That's not so good to use. That's the standard we use. That's the quantum random number generator. But and also that how about today? How about today is that a few months ago, that I again to try in the 5 qubit system and to try to use to apply the same thing. That's compared to the 3 years, that's the fidelity was also improved. That the gate number was developed, and also the quantum volume, and this is one of the systematically that's the quantification of how much hardware it's good, or quantum computer is good or not. Was involved, improved. Oh, this is many, and also the T1, the T2 time was also improved. Oh, this is a good system. Then we try to that again. But I try to that again. Unfortunately, this is kind of some of the result. It's almost same of that system. In now is and that's how to say it. That's orange color. In some of the tolerance of this statistical error bar noise of this unbiased output case. But unfortunately, within this tolerance region, only 1, 2, 3, 4, 5, 6 qubit, 6 result only. Otherwise, it's any system, any output is outside of this region. Then this is also still noisy result, unfortunately. It's okay. We have already known that's some of several of the tests of the should random number generator the case. This was proposed. Needs to propose tests, several kind of the tests of this machine. In the previous results in that 20 qubit machine. 20 qubit machine case. We try to some of the stuff. We apply this each qubit in passing through this test suite or not. That's the test number is only selected 8 test. Honestly speaking, much more test is required in that to passing all tests passing through on under the hypothetical testing program. But unfortunately, the red color is just a simulated result. Simulated result, just any kind of this in above to the red one. But unfortunately, blue one is just a failure probability of this sample. Okay, this is several kind of tests. Any kind of the test below the one, below the red point line. Then this kind of the scenario, that all tests was held. That means physical random number generator check test suites are needed, or just another kind of needs to test. Our algorithm is essentially probabilistic structure, but unfortunately, it is easy to hack. our probabilistic structure in that sense. But that's okay. That's the idea should be changed. That's noisy result. Noisy result means also noisy output. Noisy output means is that some of the review of this quantum computer is that some noise or some of the sick structure. Sick structure means in that not so good, not so good or not, or just good monitoring or not. Good sort of long time stably operated or not. That means the monitoring on to be applied this the noisy output structure is that might be reveal of the hardware information. That means that my idea is based on the change in the mind using this simplest algorithm in that means on the quantum random number generator can apply monitoring on the quantum computer. That's why it's that one possibility, another feature of this quantum computing devices. That functionality is the repeatability. Repeatability is so important. Even in both computation devices, essentially on the quantum computing devices is essential to have in the repeatability of this function. This is because due to the probabilistic structure and the probabilistic output of the algorithm, we need to take the repeated circuit so many times. That means short time distance, even the short time distance, repeatability is the same output, same operated system or not. It's that's so important. Or computer in general is that the different circuits are properly operated in any time. That means also that any time, okay, today I operated on that's the 1+1 in current computer. It's okay, output is a 2. Is tomorrow is also that's the same result. This is the hopefully that's functionality is required. In the any time in that any time in that the computer will be used, hopefully use, and that hopefully use mean on the hopefully and also that's safely use. Safely use mean on that's today's, tomorrow, day after tomorrow. That's almost always same result will be output. Then that's the properly means on that's the repeatability is also required for a long time. Then that's I will check on the stability check on the for long-term stability check by the quantum random number generator. That means it's just this kind of a circuit in the as already proposed. This is a 20 qubit machine. In that a long time ago, a 20 qubit machine pocket C in that IBM provided. It's that was used. We apply so many times in that n time repeatability. And that's okay. Sample number is that so many sample we can get. This is that means sample number versus the number to obtain the 1. That's the proportion of the 1. That means, of course, ideally it's a 1/2. Means also the sum of the sum number n is just n/2. That's line is ideally operated. This kind of sample number increasing, that means this corresponding to that time proportional is that will be changed. Then, but unfortunately, that's requirement of this in output is that 0, 1, 0, 1, 0, 1. Then that's randomly generated. Then finally we can get. That's a differentiation in time. That's the now is the next slide we will put each qubit system. That's the result in that IBM Q machine. It that was executed. It's that 5 days operated in that same algorithm, same procedure, anytime. And that's from this one, checking the current status of this of the 20 qubit machine. That's differentiation or qubit number 0, 1, 2, 3, 4, 19. Then okay, this kind of result we will check. That's how we focusing on that 3 qubit. The first one, this is the qubit number 0. Qubit number 0 is that okay. In that the color is that the day is a change. They change in that 24 hours that the reverse reset. Is that the blue, orange, green, red, purple. That's kind of the day 1, day 2, day 3, day 4, day 5. And also that's the sample number is that was shown. It's here. Then that means the job number is that day by day was changed. This is because that's the sum of this cloud service is not so every time in that some of the waiting time for the wait queue for that many people want to use that machine. Then that's we have to change. Unfortunately, that's not so mandatory use. Then that's we can change on the sample number is a day by day. Such kind of cases in the qubit number 0, always 0 means that always any days. This is that idea, almost ideally operated. That's what we have already known. That means also long-term stability has this qubit. Qubit number 6. Qubit number 6. Every day is that the calibration. Even if that's the changing of the every day is a calibration. Stably operated, but not ideally operated. That means also this is because that will not be same to the number equals 0, but some of the linear structure we will see. That means linear increasing. That means stably operated. Stably operated, but an ideal solution. That's the qubit number 6. How about the qubit number 17? Qubit number 17 is that the purple color is that okay, this is the ideally operated. Red color is that the accidentally some of the number of this wave event. That means on the some of the no calibration on this day by is within it's a 24 hour, but some of the accidental reason, some of the change of this structure. And how about the green line? Green line as well. Green one is also the sum of the bent to twice. That means on the some of the unstable operation happen. In that some of the parallel operation of this system. This is that some of the visualization 20 qubit machine. This we can some result tells us to the hardware stability of this system. That's now is I'm writing the paper. This is how to quantify it on this stably operated or not. That's I want to call is a stability benchmarking or not. Such kind of I'm looking for the proper words. There's how to call that stability structure or not. And also that's the correlation structure of the temporal correlation of that we will check. That's inspiring on the classical standard check of the random number generator. This type of hypothesis testing problem. That's the sequence of the x1, x2, x3, xn. This kind of the null hypothesis xi is independent output or not. That means on the some of the next sequence of this output, that means xi O plus xi plus L, xi L is equal 1 cases, now is considered. It's that's the mixing on this output. This repeated structure, that means also that structure, this is dependent. For example, 01, 01, 01, 01, 01, 01, 01. That's the cases some of the temporal correlation has. But unfortunately, it's that there's some of this sequence on the unbiased output cases is extended. Such kind of the p-value was created. Such kind of cases, L equal 1 case test is unfair, is a fail. The temporal correlation was detected. Such kind of procedure we will check. That's the 20 qubit machine. That's the same result in the previous slide I introduced. Such kind of cases, and that's the job number. Each job is that the temporal correlation has 1 up. This kind of structure we were seeing. Its test is has passed means on the sort of less than p-value less than is 0.05. 0.05 is the sort of blue and the sort of black structure. But the black structure is that's only this. That means that the temporal correlation has normally. Then that's the correlation, also the failure ratio of this hypothetical testing coupled to we think that's the average temperature, average T1 time 1. That means that's the initialization or not of this that's a structure. But unfortunately, according to this result, this temporal correlation might not be come from that's the non-perfect operation on the initialization. That means it's another kind of the fact we have to looking for. But unfortunately, we do not have any information at all. And also, some of this, I will skip this one. And also, that's an error correlation correlated on a quantum random number generator. It's also that this is a good system, a good bit check. For example, so the ideal cases, GH state is what proposed, was generated is such kind of structure. In that probabilistically, it's that 0, 0, 0 and 1, 1, 1 is that half and half, ideally. But Adamau gave C note how to create this state. We applied this first qubit to Adamau and also the second qubit to the C note to compare to the first and the second one, and also that again to the C note gate. C note gate normally is that's the noisy. In that this is because the 2 qubit system, a 2 qubit gate has a noisy operation compared to the single qubit gate. But finally, we measure of the each qubit and the 0 and 1. Of course, some of the flip in that some of the due to that noisy operation. Final result is 0, 0, 0 or 1, 1, 1. That's the case. This is the ideal case. 0, 1, 0. That's the case. This is a 1-bit flip or 2 qubit flip. That's finally the majority board of the 0 and 1. That means also the 0 in the odd number qubit cases. That's the majority board system will be applicable. That means also that's as a merit on the elimination of the readout error of this quantum computing operation. But unfortunately, usage of the C naught gate is that's the mean of the noisy operation. That's the relations balance point on the pros and cons of this structure. Then increasing on the number of this that is GHG state. Some of the point, majority not so good random number generator. It's not so good. Then we now is that we try to check that's the GHZ state. 1 means on the only Adamao gate, 3 qubit GHZ state, 5 qubit GHZ state, 7 qubit GHZ state, 9 qubit GHZ state. That's the several kind of the some of the lands. And that's many times repeated. That's only the same days. This is because that's the different days, that's the different output procedure was proposed. Then that's we tried to that 4 years ago. Such kind of case, Shannon entropy cases. A Shannon entropy is should be 1. This is the most unpredictable random number generator. But unfortunately, mini entropy that's much more sensitive. This is the almost same indicator of this random number generator. This is a 2 indicator of this to be applicable to random number generator output. Then that's the 5 or 7 qubit. This is because that's as we expect, that's the sum of the increasing on the Shannon entropy from GHZ state 1, 3, 5, but 5 to 7 is almost same. But from the 9 qubit GHZ state slightly decreasing on the Shannon entropy and also the mini entropy as well. That means 5 qubit or 7 qubit entanglement is only this as a resource of this specific purpose to be improved of this random number generation of this 5 or 7 qubit is the maximum number of some entanglement state. That's kind of the hardware information we can get such kind of structure. Then finally, is that I would like to conclude my talk. This kind of the quantum random generator maybe tell us the current state of a programmable quantum computer. That's which was taking as the system identification problem. That's, for example, stability or temporal correlation, and also the spatial correlation as well. And also that the current quantum computer available superquantum computer does not provide the good random number generator, unfortunately. This may be not be taking as a true probabilistic machine. Why do we need it? That's such kind of structure. This is because that's the some of the cartoon of this rough cartoon of this structure. For example, is that the generator, okay, this is the over the here, we have our random number generator. For example, that's the kind of thing. This is the crowd system is also that's applicable. This is the okay, that's the IBM provided to us or just several companies provided us the cloud quantum computing. But unfortunately, that's the opening on that's the system. Some of the human being is that reveal. That's the human says, are you sure that's random? That's the problem is that the randomness you can never be sure. That means on that we need it to be to avoid it such kind of daemon. That to avoid it such kind of daemon, we have to check on the true random number generator or not. That's it. Thank you so much for your attention. You are listening.
So thank you very much, Shikano-san, for a really outstanding talk.
Yeah.
Any questions? Sure, so there would be some questions, I think.
Yeah.
Hello. Hi.
Yeah.
That was a very nice talk. You gave us good insights into quantum random number generators.
Yeah.
I quickly would ask a simple question. When you say temporal correlation, you mean the qubits are correlated over time. Is that what you mean?
Yeah.
So
That's structure. Yeah.
Okay. So does that mean non-Markovian kind of noise?
This is a good point. This is we do not have any check on the Markovian noise, no or not. That's to explain on the such kind of structure. I think in that the non-Markovian noise structure is needed, maybe. But I'm not sure that's the another even that's a Markovian noise that's kind of in that the noisy output will be explained or not. I'm not sure.
Okay. So you sort of detect this kind of correlation is what you say.
Yeah, that's only this.
Okay.
Yeah, but this is a good point. We have to bridge to the theoretical background structure of the qubit repeated operation, non-Markovian or not. Yeah.
Okay. And one of the slides that you showed, you had you tested the random number, the randomness by finding the frequency of number of ones. And you said if it is uniform, then it's a good random number, good enough random number generator.
Yeah.
But
yeah.
even when you have a noisy case where the noise is of the type of depolarizing noise, even then you can expect to get this kind of uniform behavior, right? Would you say then?
Yeah.
Would you still call it a good random number generator when it is noisy this way, where the noise is due to depolarizing?
That's a good point. This even that's the polarizing noise that's the completely to the mixed state. If that's the case, that's the same result we be expected. But that means on the non kind of that's the non-quantumness standard we wanna train. That's a non-quantumness of such kind of amount. But unfortunately, even in that result, we cannot expect it. This is because that's the recently structure, that's the output. It's not be explained on this structure. That man is that not be some of the partially on that quantumness that's required or not. But as I explained to that such kind of system, such kind of error correlated to the quantum random number generated generation case. That's even if the depolarizing noise, that's the merit is that everything is eliminated. Then that's the monotonically increasing on the number of the qubits of this GHZ state. That's the monotonically decreasing of this of this. That's the result.
Okay.
But now is the result is a slightly at least that's the past several qubits that's increasing. That means on that quantumness some of this some of the even that the depolarizing noise that's some of this structure has, but but in that's not so perfectly operated. That's some of the balance in that we have known now. This is a good still also good point. That's a bridging structure in the physical modeling of this the T1 the T2 model, and also that's our noisy result.
Okay.
Yeah.
Okay. And lastly, just continuing with what you said. So entanglement is a resource because it allows you to identify noise. Is that why you pick entangled states to study randomness as a resource for randomness?
Sorry, that's this not so good to explain to that this kind of the work. It's that's maybe on this so many qubits on that some of the entanglement the structure is any kind of quantum computation. The assist as a system quantum how many entangled qubit is that available we use. Available means on that usefully use as a resource of the computational resources. But unfortunately, nobody knows how to check on this easily to check on that such kind of system. Then that's why I firstly propose to such kind of case.
Okay.
This is my motivation, but unfortunately, that's the results as a slightly said in the sort of already sort of 3 years ago, then that means that's the work was stopped. This is because the no bridging, as you pointed, on this physical modeling on this qubit noise model, and also that our result that's a misbridge. That's why it's still unpublished on this our proposal.
Okay.
Yeah, but when you have any interesting on that, please let me know. That please collaborate with that. I'm very happy to collaborate with that any people on
Okay,
this.
sure.
Yeah.
Sure. Thank you. Thank you. Thanks for your patient explanation. Thank you.
Thank you.
Okay, any other question or comments for Professor Shikano? Okay. All right. Okay, so
Yeah.
I think there are no more questions.
Yeah.
And so would like to thank you very much.
Yeah. Thank you.
It was a really very nice talk. And
Yeah. Thank you so much.
yeah. So we are beginning to use quantum computers, including quantum annealers. And so we will keep you, informed about our progress, and hope to interact with you on a regular basis. And so again, thank you so much for your excellent talk, Shikano.
Yeah, thank you so much. It is my great pleasure to give the talk.
Thanks so much. Thanks.
Yeah, thank you so much. This is you are still 3 p.m. right now.
Yeah, it's 5 minutes past 3.
5 minutes past. 5 minutes past already?
3.
5 minutes past the 3.
Yeah.
Okay, good. Okay, this is a good day, hopefully.
Yeah, it's a nice.
And also finally resolving on this COVID-19 quantity time we will meet with the face-to-face, hopefully.
Yes, sure. I think maybe next year, I guess. Okay.
Yeah, hopefully I would like to. I'm very happy to go to.
Yes. I think we'll have to invite you to visit us once.
Oh, this is a good proposal. Yeah, for me.
Okay. Then.
Yeah.
Thank you so much. Okay.
Thank you so much. That's
okay,
great.
Thanks.
Yes.
Bye.
Thank you, Shikano-san.
Yeah, thank you. Yeah, thank you, Asaki Sensei.
Okay.
That's Asaki Sensei came. That's last month actually.
In that room,
That's my room.
yeah.
Yeah.
Okay.
This is Asaki Sensei. Lives in the near here actually.
So,
Actually,
yes.
this is not a good one.
See you again. Yeah.
See you again. Yeah.
Okay.
Thank you.
Yeah. Thank you.
Yeah.
Bye.
That's it okay?
Yeah. Okay. Yeah.
Thank you, Das-san.
Thank you very much
for inviting me to this interesting talk.
Oh yes.
Okay.
It's our pleasure. Thank you.
Yeah.
Okay.
Okay.
Okay then. Bye.
Thank you so much.
Thanks so much. Bye.
Yeah.
Okay, bye.
Thank you a lot. Yeah.
Yeah.
See you then.
See you.
Yeah.